Hey folks, happy Saturday. Let me get a few things organized here and we'll jump right in. All right, it looks like everything's coming through. I think since the changes in the video setup, which is we have the black bars on either side of the screen here, but seems to be working and not freezing, so we're going to stick with that for now. And then the audio seemed to be sorted out last stream as well. So I think we're all good to go. As always, please feel free to jump in the chat, say how you're doing, say what you're up to this Saturday, or feel free as we're going along today and what we're working on to offer feedback, ask questions, etc. And I'll continue to do my best to check periodically in the chat. And apologies if there is a long delay. So I wanted to start off today. We're going to talk about what we're going to work on, and we'll do our usual thing where we kind of create an outline and try to stick to it a little bit. But today, kind of what I'm thinking about in terms of working on MOS, which is the processor and ultimately full vertically integrated computer, we hope, that I'm building, is the breadth of things that are included and kind of like my desire to know everything about all of them and how that's kind of like impractical and unproductive at times, but also not wanting to kind of squash that desire, right? Because I think it comes from a good place. And I think this applies in a lot of different areas, but that's kind of top of mind for me today. Once again, wanting to like try to focus and drive forward the things we've been working on specifically. Recently, the instruction decoding and kind of like going really deep in the weeds on that and reading through the RISC-V spec, which we're going to do some more of that today. But also knowing that, you know, if I took a little bit less time to understand it all, that we'd probably move a little bit faster. But right now, since this is not a commercial endeavor, I actually feel okay about the level of depth, and I think that's part of the value that we're bringing here. So anyway, that's just kind of what's on my mind today, and hopefully we're going to continue to keep this something that remains enjoyable, and I'm able to go into a lot of depth on, and hopefully that's useful to folks, but also want to be productive in moving forward. So anyway, top of mind. Let's go ahead and get into working on a few different things, maybe recapping also what we've worked on the past couple of streams. So what we're looking at here is on the left where we've been documenting all of the RV64i, actually, sorry, on the right where we've been documenting all of the RV64i instructions, basically just pulling those out of the unprivileged spec for RISC-V. So we have RV32i, which is the 32-bit base integer instruction set, and RV64i is basically just a couple of additional instructions / modifications to instructions. So it's really not too much else. You can see that we are just updating register immediate and register, and then load and store instructions. So last time we were actually looking at control and transfer instructions, which are not changing at all. So pretty straightforward, but we have been taking time not just going through and understanding how they work and what the format is for each of them, and what the specific fields are in that format, but also documenting what the control signals are for each type. So let's go ahead and I'm going to talk about this in a minute because it follows on where we were at last time. But I'm going to open up Excalidraw. Cool. And it still has some of the stuff here, which is great. Nice. Okay, so we have our instruction decoder, which is kind of what we've been working on. And then we have our control unit, which we're sending in. Basically, if we have, let me change the stroke there to black. All of our instruction formats, which we can look back over here, they're basically shown in this style. The lowest 7 bits here, the least significant 7 bits, are the opcode, and we've been looking at all of the instructions that are supported in this table here. So if we look at the opcode, one of the things we'll notice is that the two least significant bits of the 7-bit opcode are always 1, 1. So we actually don't need to feed those into our control unit, into our decoder. So we have 5 bits that are coming in for each of them. And from these 5 bits, we have control signals that we want to generate. So over on this side, we have control, and the control signals, let me finish documenting what we were just saying. We've got this and our opcode here. And we'll go back to the fun Excalidraw font here. We have our opcode, and we're going to take our 5 bits from the opcode and, bring them into the decoder. And, well, let's see. Hold on one sec. We have our decoder, which is the control unit really is our decoder. That's what we're saying. Or rather, we have our decoder, which is going to take some inputs and produce various fields like RS1 and RS2. And then the opcode, or the 5 bits of the opcode, are going to come into here. So basically 3, 4, 5. And then we want to produce some number of control signals. And the control signals that we have are listed here, or with more, let's close this for a sec. Close the wrong one. More explicitly up here. So branch, memread, mem2reg, ALU op, memwrite, ALU source, and regwrite. And so these are all going to come out of our control unit. So basically have, a number of control signals coming out of here. I won't draw them all. And last time what we were looking at is most of these are pretty straightforward. So it's like if the instruction can result in a branch, right, then we want the branch control signal to be high. If the instruction says memory address to read, we want memread to be high. So we can kind of look at all the instructions and know those in a pretty straightforward manner. The one that was a little more tricky was the ALU op. And I think revising this even might make sense. But for the most part, it encodes the operation the ALU should perform. Or we bring in the funct fields of the instruction if there are some present, which, for example, let's look where our register. We have funct 3 fields, for example, in all of these. And here we have some funct 7 fields as well. So anyway, those get passed in and maybe indicate also what the actual operation the ALU should perform is. And the last other bit that we were talking about previously was the unconditional branches. So basically where we are doing a jump. So control transfer instructions, unconditional jumps. So we're talking about our JAL jump and link and the corresponding pseudo instruction J, as well as the jump and link register. So in these, right, we are always branching when the instruction comes in. And we had looked at for something like branch if equal. So if we go down here and say BEQ, for example, we need to perform an ALU operation, a comparison, to say, hey, are these two values equal? And if so, that indicates whether we increment the PC by 4, the program counter by 4 bytes, which 4 bytes, 32 bits, all instructions in RISC-V are 32 bits. So are we going to do that? But in the jump case, we're not making any comparison, right? So we kind of want to just disregard what the ALU is outputting. And so we had drawn, I guess that was on a different Excalidraw, but let's say we have the branch target calculation here. So we want to calculate that, and we get some value here. And the output of the comparison, if it's a conditional jump, is going to be coming from the ALU. And we also have our control signal. So actually, it looks something like we want a multiplexer here. Mux. And we have our branch target, and then we also have our PC plus 4, so just our default, if not a branch, coming in here. And basically, we want to select the PC plus 4 if the branch comparison is, I think, 1 is what we said. And we want to select, we want to select the calculated branch target if the branch comparison is 1. And we want to calculate, use PC plus 4 as the next instruction if not. Let me double check that. Actually, I'll go ahead and bring up these slides here, which is what alludes to what we were talking about last time. I think it was at the very end. And these are from University of Pittsburgh. And they're talking about MIPS here, but it's a very similar model to what we're following. So here, for example, is where we are calculating the, well, let's see. We have our jump address calculated here. And this is where we are calculating the address if I think for a conditional branch. We can take a closer look at that in a minute. And then we have our, you can't see it here, but we have our branch control signal, which is coming into this AND with the comparison out of the ALU. So actually, my drawing is off here. So let's say we have our, see if I can draw it real quick. That is heinous, but we'll go with it anyway. This is truly gross looking. But let's say branch equals 1. So branch is high, so this is a potential branch instruction. And then the comparison, which is the 0 signal, which we should be able to see here as well. The 0 signal coming out of here. If they're both 1, then so if we can branch and it is 0, the comparison is 0, then we want to select the branch instruction. And if we are not going to branch, right, then the branch signal, if there's no chance of branching on a branch instruction, then this will always be 0, and we'll select just PC plus 4. But the jump instruction here was basically saying, hey, well, we want to always jump. We don't actually care about the output from the ALU here. And so what I was wondering is, do we give a different signal to the ALU to change this output to select PC plus 4 or not? But what you can see here is they're just adding another control signal for jump. I don't know if we have to do that necessarily. I haven't done the full breakdown of it, but that's just what we're going to use as well for now. So I'm going to change what we had last time. So I don't think we had that one, but we had a different, and we'll just put it here, jump, and it's going to be 1 bit, high if branch, if unconditionally branching. So for JL and JLR, that would be the case. So let me jump back over to the ISA. And let's just add that into all of these. So these are all going to be jump 0 for register ALU, and let's just find all the control signals. ALU immediates, right, still jump 0, and load instructions, jump 0, store instructions, jump is 0, B format, conditional branching instructions, jump is 0, right? We're only going to branch based on the branch signal and the output from the ALU. J format instructions for jump and link, we want jump to be high. And I think that we didn't do jump and link register yet. Yeah, and then here is where I noted it. I'm going to move this. So ALU op is actually a don't care, essentially. I'll note that down. We don't care about the ALU and always branching. So I want to take another look back here quickly. Yeah, okay, so this is the conditional branch, or okay, this is PC plus 4. So PC plus 4 coming up here, and then we're calculating the, so best way to label this, and maybe, let me just see if I can copy image, and we'll put it over here in XCalDraw, maybe. Ooh, that is tiny. Should scale, nope. All right, we're just gonna do this the somewhat gross way. So we'll take this, and I just wanna draw some of these. So I need to turn the volume down on the machine here. All right, that's better. So if we want to label some of this, this is the PC relative branch target. Up here. And this one is just PC plus 4. And this one would be, let's actually look back at some of our conditional branch instructions. They are essentially not conditional branch, 12-bit immediate B encode signed offsets multiples. So it's added to the address of the branch instruction. So that one is also PC relative, but we're adding it. Whereas let's see. The offset sanction added to the address of the jump instruction to form the jump target address. Okay, so we're added on the unconditional jump as well. Sign extend. Could also be that the MIPS instruction here is different. So in this case, this should be our PC relative branch target. And PC plus 4 coming in here. Instruction 0, yeah. Let's see if it actually, J, let's see if we can look at the MIPS jump instruction. Yeah, so we're concatenating the higher order 4 bits of the PC. Okay, so that makes sense where we're concatenating here. So I believe we just don't need this. We are going to be using this same result no matter what. But in our case, we have that result, or PC plus 4, and so maybe we don't need that jump instruction. Maybe we can do this in the ALU, but it does seem like we essentially do want it. So if we got branch and the ALU as one signal, we might just need one mux here. So maybe we could, in this case, this will be one, oops. This will be high. And we're basically saying that here we shouldn't care about the ALU result because we're not doing any comparison. We want the ALU result to always be 1. So is the ALU result 0? Yes, then it's 1. So we can either, I guess what I'm getting at is we can either force this to always be true, and so that we select the PC relative branch target, or we could have a separate signal where we have basically an or, right? Where we're saying if we have the if we have the ALU tells us to branch, or we're just forcing a branch. So the logic looks like, let's draw it over here again. Try to use a smaller stroke this time. So and then or, and if we have coming into here branch signal, and we have the 0 from the ALU, and then we have jump coming in here, and I really need to just turn on the elbow. Oh, it's already on. Perfect. So the result of this. So this in the case of, well, let's just take this and duplicate it a few times. So on a conditional branch, we're going to have 1 and 1 or 0, and we're going to have 0. And then on, so this is a conditional branch, this is an unconditional branch, we're going to have 1 and 1 or 0, and we're going to have 1. which means that this is always 1 because we don't care about this output. In this one, it's 1 or 0, right? Compared, and the target is this. Cool. So I think that solves the issue. That feels to me cleaner. I'd like to get more kind of like input on whether using the ALU for this example, like forcing the ALU, makes sense. I don't think it does, right? Because we're basically making the ALU do something. It's meant to be an arithmetic logic unit, right? And we're basically making it do something that it shouldn't. So I think that's kind of the key here. Cool. Let me jump. We have the JFormat instructions, jump and link, and that's JAL, and then I was going to add the JLR here. Sorry, back up here. JALR is I-type. And I was also going to add the note, the value of ALU op is inconsequential when jump equals 1, regardless of the 0 output from comparison. We will always take the branch target address. Okay, so for some background on this, the textbook that this is kind of like based on is the Computer Organization Design. If you've ever been on the stream, you've definitely seen this before. And in the textbook, it basically stops short of talking about unconditional jumps. And I'm actually just double checking that right now. But the diagram looks very similar to the one that we're seeing from the University of Pittsburgh there. And one of the things I was missing last time was the fact that we had the separate ALU for, I'm just double checking here. And it's not an ALU up at the top. And maybe, I think I misrepresented that. Let's go back. This is an ALU, right? This is just an adder. And okay, so let's fix up our to-dos here for today. Get all of these. To do. Oh, we did get this one done, so that's great. Haven't done that. Still working on RISC-V instruction decoding, but to be more clear, add JALR documentation to actually decode some instructions in Verilog. 3, write a test bench for control unit. And 4, well, we should say write the control unit, right? Control unit, this is sort of like instruction decoding. Let's see, the other thing I wanted to do, it evades me right now. So we'll just do this. So jump and link register instruction is I type. AOU immediate instructions, jump. Let's just take this. Load instructions. Indirect jump instructions. I don't know why I called it. Oh, okay, yeah, indirect jump instruction. So let's finish this to do. And I'm going to grab the control signals and the opcode, and we'll make sure to populate those. And the opcode is, see, for jump and link register here, 11001111. Cool. By adding the sign extended 12-bit I immediate to the register RS1. Okay, so the indirect jumps do matter. So if I had read ahead, that would have been useful. So we actually do need something similar to this. It's not, the jump instruction is not the same. It's not PC relative. This one is PC relative, right? We're adding, but the input is going to be from RS1. So here, let's go ahead and make sure to add this down. The 12-bit immediate is sign extended it's the least significant bit. PC plus 4 is written to RD. And func3 is just 0. All right. jump should be 1. And we'll grab this. Mem_read 0, mem to reg 0, and let's see. We do have write back though, because we need to write PC plus 4 to RD. Which is, I don't think that's shown. Here are write data coming in here. It is only the ALU result or the, yeah, it's only the ALU result or the value read from memory. So reg write should be high. ALU source high if the second operand is immediate, low if second operand is from register. I guess we don't care, right? RD, we should care. And ALU source as well. Mem to reg 0. So what I'm thinking for the writing the PC plus 4, yeah, so basically this value needs to be okay, so we can, it is the ALU result, right? Because we have RS1 coming, so let me just keep with our RS1 is coming in. Oh man, there we go. RS1 is coming in, and then the immediate, right, is what we're adding to get, and then we mem to reg is 1. Okay, so I'm off here. Mem to reg is 1, and we do care about ALU source and ALU op. ALU op should be add. Although we also have funct3, so let's see if jump and link register. Yeah, nice. Okay, so we could just stick with 1, 0, right? And note that it matches add immediate. So I have all kinds of issues here, and we're going to correct them. So mem to reg is 1. We do care about ALU op. We're going to say 1, 0. And reg write. ALU source is going to be 1 as well, right? High, the second operand is immediate. funct3 matches add and add as we are instructing the as we are also performing an addition operation with JALR. That's kind of stuff that I feel like but that's not what gets written, right? So I think it is interesting. We are going to perform an add. Are we going to use the ALU for that though? Because, so I was mistaken there, because the RS1, right, is going to have, we are going to be performing an add with the immediate in RS1, but that's not what's getting written to the register. The unconditional jump instructions all use PC relative addressing to help support position and independent code. The jump and link register instruction was defined to enable a 2-instruction sequence to jump anywhere in a 32-bit absolute range. Let me look this up. PC relative addressing. Make sure I can refresh my memory here. We should load a register with value stored in program memory a short distance away from the current instruction. So how is jump and link register PC relative, right? We're not using the unconditional jump instructions all use PC relative addressing to help support position independent code. The jump and link register instruction was defined to enable a 2-instruction sequence to jump anywhere in a 32-bit absolute address range. a load upper immediate instruction, load unsigned immediate. Wait, no, sorry. I think that is load upper immediate. All right, it is load upper. Okay, cool. I was right the first time. All right. Yeah, we haven't gotten to those yet. It's like in the conditional branching, we're added to the address of the branch instruction to give the target address. So that makes sense. In the jump and link instruction, the offset is sign extended and added to the address of the jump instruction, right? The indirect jump instruction, jump and link register, uses I-type encoding. The target address is obtained by adding the sign extended 12-bit I immediate to the register RS1 and setting the least significant bit to the result to 0. The address of the instruction following the jump is written to register RD. So how is that a PC relative addressing? This is an unconditional jump. Let's see if we can find anything on it. PC relative. So is it just saying because if we are using two addressing instructions that allow these modes to be ample and efficient? RD to the sum of the current PC and a 32-bit value with the low 12 bits of 0 and the high 20 bits. The instructions are essentially the same. They both take a U-type immediate, i.e. the high 20 bits of a 32-bit quantity, and add something and produce the result in RD. The difference is that load upper immediate adds the immediate to 0, while add upper immediate program counter adds the immediate to the PC. Sometimes it's easier to think of the two addressing modes as PC relative and 0 relative, as that makes the distinction more explicit. Okay, so maybe I'm reading too far into this, right? Maybe we're just saying that we support PIE, position independent code, by using PC relative addressing. Yeah, okay. A load upper immediate can first load RS1 with upper 20 bits of a target address, then jump and link register can add in the lower bits. Similarly, add upper immediate program counter, then jump and link register can jump anywhere in a 32-bit PC relative address range. So idea for a blog post or similar, look at disassembly. That's not correct. Disassembly of program when using PIE versus not. Didn't realize I had the opacity of all these down. Blog idea. Okay, I also want to add that note. Here. RISC-V addressing modes. Oh, this is such a good series from, oh, they don't have the name of the person. Palmer, I believe, wrote this. This is a really, really great series. Would highly recommend. So we have, see this post for more details. Addressing modes. So we have register offset, okay, and absolute. What is this, register relative? Yeah, register offset. Yeah, that's. AU IPC. Well, let's see. Jump and link. AUIPC plus jump and link register, and then the branch instructions, or the conditional branch instructions. So register offset is just jump and link register. And this would be load upper immediate plus jump and link register. I think that actually differs in what this is saying here. Okay, yeah, it's saying combining with. Jump and link, I feel like this should be AUIPC plus jump and link register, but that's fine. Cool. I feel like we still left it hanging a little bit on the fact that we need to get our, in the case of any PC relative or any branch, right, we need to write PC4 to do write PC plus 4 to RD on branch instructions. So I know that branch is considered here, though. So I'm a little confused about how it's not represented. Because write data only comes from the selection of the ALU output and the memory read. Let's see if we consider it. I'm also looking at the textbook I have here. It appears to just not be considering it. Well, we've got our to-do. Okay, added jump and link register. Okay, another to-do is adding descriptions for all these conditional branch ones. Actually, I'm going to go ahead and do that. Apologies for the painful observing. So, is not equal. And then branch less than is RS1 is less than, yeah. Greater than, okay, cool. Filled those out. I think I had a couple more that were maybe missing. No, stores look good, loads look good. So this is not entirely true anymore because we do want to jump, but we want to use the output. We do want to use the ALU, I believe, when we're comparing to the registers. So this is not necessarily true. All right, I'm going to, let's see, what branch are we on here? Just gonna push those up. I'll fix the commit messages later. I just want to make sure that we have those good to go. Jump over here. I'm gonna check and make sure that the updated formatting looks okay. I can kind of get rid of the all have the same opcode. And so I want to change the decode unit though to, well, first let me jump up here and say, we'll just say opcode like the others. And then on decode, we'll call it control. And wait, we want control tb dot v. And output reg jump, and we'll call this opcode. And we only need 4. And I'm going to switch this to the normal style here. Note. right, some of these I added, but we don't need quite yet. Let's pull up, and we can just go through these. Local param, opcode. B 01100. Do we already have that? Opcode op. All right, these are. I'm just gonna get rid of these for now. R format. Let's say ALU RR, and we'll say ALU immediate. And sorry, I want to go. We'll do it this way. Oops. Opcode. And we'll say ALU RR and branch jump equals 0. Memread is 0. Mem to reg 0. ALU op 10. Memwrite 0. ALU source 0. And we'll do one more. And then I want to get our test bench going. 0. Okay, branch, jump, memread, mem to reg, ALU op, memwrite, ALU source is immediate, and then reg write. Okay, those make sense. Okay. Control test bench. So I've been using, I guess the background information here is I've been using Verilator, but that is not easy to use with, let me also make, yeah, okay, cool. That is not easy to use with Vivado. And I also just honestly don't have a lot of experience with the Verilog test benches, so I just wanted to get into doing that. So we have our latch module. Oops. We'll call this control. I really love this format here. I initial. So we're not going to take anything into the test bench. And then we'll say in module and this is unclocked, so we'd just be testing the logic. I'm kind of questioning whether it's really even super critical until we're fetching the instructions. Well, I guess we can do it regardless. Let's see. Control. And let's just make it the yeah, a register ALU, and we'll give it opcode. I think we can. Well, I guess these can just be wires. No, they yeah, they can be wires. Jump. Oops. Branch. Jump. Mem read. Mem to reg. ALU. Op. Mem write. ALU. Source. Reg write. So we could run a clock and just change it. But we're not actually passing the clock, so. But I think we can use it to just delay the changes. So let's give it a try. Initial, begin, yeah, and then end. And really, these should all be indented. And it was just a register for the clock. think it was invert the clock. So right, clock is 0. Forever on 1 picosecond. Or 1. And is it clock at 0? Oh, okay, clock starting value, yeah. For every picosecond. I think this is effectively the same thing, but we can just do the same thing here. And so let's just start out with okay, monitor is pretty neat. So I really want to monitor all of these signals. What is the formatting? Equals percent B. Okay. Let's just try 1 for now, and 1 that will change. ALU source is a perfect example. Time. Let's see, we said time and ALU source. And let's just say opcode equals. We'll just switch between them. Cool, yeah, and that's the delay. Okay, let's see if we can get Vivado open and go from there. Wow, already an hour 22 in. All right, and I'm going to need to open this back up. So, still have the maybe BRAM situation here. Where's remove? Add files. And we want MOS comp, MOS RTL Control. We'll see if adding the test bench like this works fine. Ooh. Non-module files. Where are errors here? Ah. Classic. Got a comma. Forever. I think my syntax is wrong for the... Ah. Yeah, equals. Not clock. Simulation. Let's say. Okay. All right. We have something here. And let's see if it's changing. It looks like no. Yeah. Value 1. Can I zoom out? There we go. And ALU source is matching up. Cool. So that feels a little bit faster to me than I really should be getting a error here on ALU op because it should be a 2. Well, it's because I didn't write it as such. Wait, sorry. ALU 1 0. I guess it just lets me assign. I don't know if it's treating these as. I might need to write. What is. Number format. It's not really a format. Here we go. Defaults to the decimal base. So we really want the binary for all of these. 1B. Oops. Let's run this again after I correct this. This 1, 2. And hopefully it gives me an error here. I wish it reported that I had an issue. Let's see if this fixes it for us. AOU op. Nice. So it's sitting at 2. So 1, 0. Okay, that's right. And I think we would get the linting issue if we actually tried to, yeah, or ran linter. That would probably work. Pretty straightforward. All right. Just wanna, we can get a screenshot for the socials. And really, let's just change this to every 1. What do we start at? 1, 1 for the opcode. Yeah, okay, cool. Okay, actually, I'm going to change it one more time, just because we want a different instruction every full cycle. So positive edge to positive edge. obviously this is like we're not fetching the instructions or anything like that, so it's really kind of inconsequential. It's just visual at this point. Whoa. All right, I'm gonna take a picture of that. I wonder if we got any of the simulation output. It doesn't look like it. Let's see if we can find auto use simulation output. I don't know why there's no simulation log. Display. Put it here. just like fixing it there. It doesn't seem like it. Well, anyway, we can tackle that another day. But anyway, let's look back at our to-dos for today. Added jump and link register. Actually decode, yeah, I'd say so. And write a test bench. So still super early. And hopefully between now and next stream, I will go ahead and get this finished out for the instructions that we have. And then we can talk a little bit about fetching instructions. And then we might just skip over branching for now and just try to do execute a few AOU instructions in a sequence and then look at the output. But anyway, let me switch over here to finish this out today. Appreciate everyone stopping by as always. Medium length stream, I guess, today. I am gonna go eat some food and continue hacking on this a bit. But I hope everyone is having a great weekend. As always, I know I end every stream this way, but if there's anything I can do to make these more useful, or you want to give me feedback or anything like that, certainly always welcome. I absolutely love digging into this stuff, even though it seems kind of tedious. But the small realizations, I think, go a long way for me. So hopefully it's useful to others. And I'll keep doing them as long as I have any signal that they are. So thanks. Have a great weekend, and I'll see you on the next stream.